please take advantage of that. So let's first look at y equals sine x. Now, because we use the circle to define y equals sine x or sine x, what you've got here is a wave. Imagine taking your circle, and as you go around, you kind of stretch it out, so you have this wave. And because sine x represents the vertical height of your circle at certain points, as you know, the distance between the x-axis and the circle itself vertically, you're going to get a certain wave that starts at 0 and goes up to 1 and then back down to 0 and then down to -1, and it continues in that manner, okay? Now, one period, that means one complete cycle that you go through has a distance of 2 pi or a length of 2 pi. So you start at 0 and you go up and down and back to 0. That's one complete cycle. And then you repeat for the next one. So that's called a period. And it also has a certain height of 1. The distance between the x-axis and the highest point is 1. That's called the amplitude, okay? So we have the amplitude, which is basically the height from the x-axis to the highest point, and then we have the cycle, the distance, which is the horizontal distance of how long the cycle lasts, and that's a period. So it's 2 pi, right? For sine, you'll see that the x value for that point is 2 pi. Okay, so that's the period. And then we can shift this around, and that would be called a phase shift, but we'll talk about that in a minute. So here's our original function. Now, can everybody see okay? I just want to make sure that you all are able to see. If you can't see, let me know, okay? So the next function that I would like to do is y, it's a variation of this, y equals 2 times sine x, okay? Look at what happens to the function. When you multiply your sine function by 2, it increases your amplitude. So now instead of 1, our amplitude is 2. And what do I mean by amplitude? That means how far does this wave stretch from the x-axis? What's this distance from the x-axis to the highest point? This height is 2. See, you can see it on the y-axis, that top hill, if you will, or whatever, the top of the wave is the height of 2. Okay? And then when it dips down, it's in a valley, and the depth is 2. So that's called the amplitude. The amplitude is a distance, so it's always positive. Even if I put a negative sign in front. Now watch what happens when I put a negative sign in front of the 2. I'm going to get rid of my sine graph here so it's not too cluttered. And so I have y equals 2 sine x. Now I'm going to do y equals minus 2 sine x. See how it flips the graph over the x-axis? So what was above is now below, and what was below is now above. So whenever you multiply by a negative like that out in front of your function, it's going to flip your whole entire graph over the x-axis, and you're going to have like a reflection there, if you will. Okay, that's called reflecting. All right. Now I should let you know that I'm remembering now what it was that my students couldn't see when I taught this on Monday. I wanted to go into the homework and show them how to use the graphing utility, and that was not showing up through Zoom. It was a pop-up window and they could not see it. So I'm not even going to try to do that. I'm just going to use Desmos here. So when you're doing the homework, there's a graphing utility embedded in the assignment. And when you click on that, it'll help you graph the function. You're going to have 2 choices. So let me just show you what it's going to look like when you pull that up. So you've got your sine x function. And it's just going to show you a piece, and I'm going to try and restrict the domain here so you can see what I'm talking about. Hold on. Just give me a moment. I think I go like this. And then I type in 0 is less than or equal to x, which is less than or equal to 2 pi. There we go. All right. So as you see here, when you pull up that graphing utility in your homework, it's going to have a little square or a little box with a picture of a wave like this. Okay? That means that you are going to, if you are trying to graph a sine function, you are going to click on the box that has this picture in it, showing you that it's a sine function. And then your sine function will appear on the screen. But before it does that, now listen carefully because I can't show you. I wish I could show you, but I can't. Before it does that, you're going to have to position your cursor right at the origin, click it. So first you go and click the box that has this picture in it. Then you go to the graph and point at the origin where you want to center it and click one click, and it will all of a sudden appear there on the graph. Okay? Then a little box will pop up, and in that box you specify the amplitude that you want. You specify whether you want to reflect it across the x-axis or the y-axis. You just do all your specifications. So you don't have to physically graph it. You just have to put your specifications in the box. All right? So that's how that works. And I wish I could show you, but like I said, my class yesterday could not see it. So we couldn't get it to work. So I'm not even going to try. All right, now watch what happens when I change this function to cosine, and instead of going from 0 to 2 pi, oh no, I want it from 0 to 2 pi, yeah. I'm just going to put cosine in here now, okay? Look at the shape of the graph. It's still a wave, but instead of starting at 0 and then going up and then back to 0, it starts at 1, dips down to -1, and then goes back up to 1. So it's shifted off from the sine function. So when you're graphing in your homework, you're going to select the shape that looks like this for cosine and then position it on your graph if you want to graph a cosine function. So it depends on what you're graphing, right? So there are two options. You're going to either pick this shape graph for sine, okay? And you'll see what I mean when you see the little boxes to the right. Or if you're graphing cosine, you're going to pick this shape, okay? And that's in section 5.5 homework. All right, now back to the discussion of how we graph these. Okay, so here is the cosine function. If I want to have an amplitude of, let's say I want -3 cosine x, okay? Now, you see that negative in front? What it does is it takes, this is a valley, right? It becomes now a peak when I multiply by negative. And furthermore, since I'm multiplying by -3, it stretches that, so the height of the peak is up to 3 instead of 1, okay? Well, the amplitude is still 3 because remember, the amplitude is the distance from the x-axis to the highest point. So the amplitude, even though I have a negative in front here, the amplitude is still 3 for this function, okay? Now, what happens if I put a constant in front of my x? So let me get rid of this function here. And whoops, I went too far. Y equals cosine. I'm going to, instead of x, I'm going to put 2x. Well, let's do both. Here's x, and here's y equals cosine 2x. So the only difference between my two functions is this 2. That 2 multiplied in front of the x, what it does is it compresses the function horizontally. So basically, when you multiply by 2, it basically means you're going through your cycle twice as fast. So instead of going from 1 over 2 pi. Now I'm going to go through a full cycle at pi, and then I go through another. So I go through 2 cycles over the course of one period, a normal period, okay, a normal for cosine. So cosine, the period is 2 pi, but if I have cosine of 2x, the period is pi. All right, well, let me go back to the notes for a second now, and let's talk about this. All right, so the pattern that we're looking at is y equals a sine bx plus c plus d. All right? What A, B, C, and D are constants, and they all have meaning, okay? The A is the amplitude, and actually the absolute value of A, I should say, is the amplitude. I've talked about that a little bit. Your period for sine is 2 pi, but when you multiply by a constant 2 in front of the x like we did earlier, we have to divide. It shortened my period because I went through 2 cycles in the same amount of a period as regular sine. I don't know, I'm not saying it very well, but so in other words, the period is 2 pi over b. That is called the period. And then I haven't talked about this yet, but the phase shift is minus c over b. And I will talk about that in a minute. And finally, d is the vertical shift. So d, if so it's up if d is greater than 0, and it's down if d is less than 0. Okay? So basically, this is what you want to focus on for section 5.5. You want to focus on A, B, C, and D, and understanding amplitude, period, phase shift, and vertical shift. Not so much vertical shift. I think the last 2 problems in the homework deal with the vertical shift, but your focus is going to be mostly on the first 3, amplitude, period, and phase shift. All right? So let's look at some examples, okay? I should probably let you finish writing on that. Just I'll give you a little bit more time to do that. And so some of the homework problems, they'll give you a function and they'll ask you questions about it. So for example, if y equals 6 sine x, okay? The amplitude is 6, so A equals 6, and so therefore the absolute value of A equals 6, and so that means that the amplitude is 6. All right. Now, the period for this one is 2 pi, okay, since our b is equal to 1. Okay, so b is this constant in front of the x. Well, there's nothing there, so it's assumed to be 1. We haven't changed the period because we haven't multiplied a constant there. And the phase shift is 0. There is no phase shift. In other words, no shift. Since c equals 0. Okay, so this is a pretty simple problem. Really, all that they're going to ask you in these type of problems is what is the amplitude, and then graph it. All right, if you need to use Desmos to help graph it, really honestly, the graphing part is fairly easy. It's just using the graphing utility in your homework can be frustrating, but you'll figure it out, okay? So the first 3 questions in your homework just ask you what is the amplitude and then graph it. And they want you to graph it next to sine x. So you're actually going to put 2 functions on the graph, kind of like I did in Desmos there. All right. Now, for the next problem, y equals sine 3x. Okay, the amplitude is 1 because the absolute value of A is 1. So the amplitude is 1. And that's because this constant in front of the sine is not listed there. It's assumed to be 1. The period, remember, is 2 pi divided by b. Well, in this example, b is, I want to use a different color here. B is 3. Okay, that's your b. So 2 pi over 3 is the period. There, again, there is no phase shift because we have not added or subtracted any constant here, okay? All right, so any questions on that so far? All right. Now, A equals 1, so the amplitude is 1. B equals 1, so the period is 2 pi. And now C is negative pi over 2, okay? So our phase shift is pi over 2. So the phase shift is the opposite of your C value, right? Alrighty, let me just graph this in Desmos real quick so you can kind of see what the graph looks like when you have a phase shift. All right, so remember this function here is x minus pi over 2 inside the sine. I'm going to share my screen, going back to Desmos. And let me get rid of this. So my basic function is y equals sine x. And then along with that, I'm going to graph y equals sine of x minus pi over 2. So pi divided by 2. Okay? And you can kind of see what happens there. So the green function is the regular basic sine function. Now, when I subtract pi over 2, this point here gets moved over here. So now, instead of the function being 0 at 0, it's now 0 at pi over 2. And the original function at pi over 2 was 1. Well, now if I go a distance of pi over 2 over, the blue function is at pi is equal to 1. So everything gets shifted to the right by pi over 2 units. So that's a horizontal shift. So I'm looking at the x-axis to see. So going from this point here at 0 over to this point, you can see that the x value changes from 0 to pi over 2. And that's the phase shift. We're shifting our graph. And notice it's a horizontal movement because this constant that's being subtracted is inside the function as opposed to outside the function. Now let's watch what happens. I'm going to get rid of this now, or I'm going to change it a little bit. What if I subtract pi over 2 outside the function? Okay, so there's my function. Now I'm going to subtract pi over 2 on the outside. You'll see what happens is it shifts the whole thing down. All right. And remember, pi is about 3.14. So if you divide that by 2, that's going to be 1.7. Let me think. Am I thinking that right? 1.5. 3.14. So 1.57. So you can see right there is about from 0 to -2 is this distance, and this right here is about, well, it's negative pi over 2, which is about negative 1.57, okay? All righty? So you can see it makes a big difference if your constant that you're subtracting is outside the function or inside the function, right? Go back inside the function and pi divided by 2, and there you have it, okay? So this is a phase shift, whereas when it's outside, it's called a vertical shift, okay? So play around with this Desmos, and you'll learn how these constants affect our basic functions, our trig functions. And all of this discussion for, let me go back to the notes. All right, all of this discussion here applies for cosine as well. So let me go ahead and write that in there. You can have the same thing going on for cosine. Okay, tangent and cotangent are different functions. All right, let's see. I want to do another example. Any questions on this so far? All righty, let's see. So we need to describe what's going on here for this graph. So the amplitude and I think I'd like to use some different colors here to highlight this. So the amplitude is minus, well, actually, this is our A value, okay? And this is our B value. There's C. And finally, there's D. I hope you can see that. All right. So What can we say about the graph? Well, the amplitude is the absolute value of A, so that would be 5, okay? The period is, okay, first off, cosine has a period of 2 pi, so I know that's going to be 2 pi, but then I have to divide it by my B value, which in this case is 4. Okay, and so that is equal to pi over 2. That's my period. The phase shift, this is the horizontal shift, is negative C over B, which in this case is the opposite sign of C. C is negative pi, so the opposite sign is positive pi. And then I'm dividing by 4. So this is my phase shift right here. And finally, the vertical shift is up 1 unit. Okay, so those 4 properties help us understand the graph of our trig functions. In this case, it's cosine. All right. By the way, just to remind you, the period for each of our trig functions. Is 2 pi for sine, cosine, secant, and cosecant. Okay, those 4 trig functions have a period 2 pi, and it is pi for tangent and cotangent. Okay. I'm trying to think of what example this is that I did. Hold on. Example 4. All righty. Any questions on that? Feel free to type something in the chat box if you don't want to say something out loud. Okay, let's see. Notice that this constant in front is negative, but the amplitude is still just 5, because the amplitude is a distance, and distance is always positive. Why don't we go ahead and graph this function in Desmos? So this time we're working with cosine. Y equals cosine of x. And then our function that we're trying to graph, which is a variation of cosine, is minus 5 cosine of 4x minus pi. Let me see here. And is it plus 1? Yeah, plus 1. There we go. So everything was shifted up 1. So if I graph y equals 1, that purple line is kind of the midpoint between the top and bottom of your function. So There we go. So from the bottom to the top, this is the midpoint. So you can see everything is shifted up 1. The amplitude is 5, so the function would have gone up to 5, but because we added 1 at the end of the function, everything got moved up 1. And it would have come down to -5, but again, because everything got moved up, it comes now down to -4. So there's that vertical shift. But then, instead of taking a whole 2 pi to go through one cycle, it goes through 4 cycles. So it goes up, it goes down and back up, down and back up, down and back up, down and back up 4 times for the original function to go once. And that's because of the 4 times x in the problem. And then you have your phase shift, which is pi over 4. And this is a cosine function. And I've not really seen the phase shift very well, probably because it's so small. Let's see here. It's really hard to see. Maybe I should change my graph a little bit here just so we can see it better. Let's take out the 5. And let's go ahead and take the negative out. And let's take out the 1. And just focus on the phase shift now. So now I'm going to zoom in here. So remember, originally we had flipped the graph, but this one is not flipped. So it starts at 1, but now because of the phase shift, instead of starting at 1, it's going to start over here at pi over 4. So you can see how it's been shifted. This high point is now shifted over to this high point. And you can see when I hover over that with my cursor, it shows me that the x value is pi over 4. So that is the phase shift. This point, this high point, has been shifted over pi over 4. And notice it's shifted in the positive direction because this is a minus sign. It's kind of opposite of what you think. If you subtract a constant, it's going to shift your whole graph in the positive direction. If you add a constant on the inside, it's going to shift it to the left. And that you should remember from when you learned this in algebra, translating functions. Adding on the outside shifts up, subtracting on the outside shifts down, but adding on the inside shifts it left, and subtracting on the inside shifts it right. So you might want to review those translation rules from algebra. But you don't really have to worry about it too much because I'm not going to have you actually graph anything for the test. And that's simply because I want you to focus. First of all, it's very hard, and you're not going to have a graphing utility, and not everybody has a graphing calculator. So I don't want the people who happen to have a graphing calculator or have an unfair advantage to those who don't have one, you know. So to keep it fair, I'm not going to have you graph anything on the test. So this is just for your homework purposes. You can use Desmos to graph it on your homework if you need help. And even your homework itself uses a graphing utility. So you don't actually have to graph anything yourself. But for the purpose of the test, what I want you to focus on is knowing how to find the amplitude, the period, the phase shift, and the vertical shift. Those are the things that you should know for the exam, at the midterm exam. Amplitude, period, phase shift, vertical shift. So you want to go back to these rules here that I showed you earlier. Know these rules. You're going to have to know them by heart, okay? The absolute value of A is the amplitude. 2 pi over B is the period for sine and cosine. And then minus C over B is the phase shift. And D is the vertical shift. Also, I am not going to ask you to graph any tangent or cotangent functions, but I do want to discuss those with you because in section 5.6, you will have to graph those. So let me take you over to section 5.6 in your homework. We'll talk about that for a little bit, just a minute here. I have a lot of pages in my notes here. Hey. Oh, thank you. Perfect, thanks. Okay. All right, so the best way to do this is to go over to Desmos, and we can see it. And like I said, I encourage you to use this utility when you're doing your homework. It'll help you understand things much better. Okay, so y equals tangent now of x. Okay. So one thing you should know, as I mentioned earlier, the period for tangent is pi. So each one of these long curves, and you might be wondering, why does it look like that? Why don't I have a wave? But remember, tangent has certain values that are undefined. And what happens when you're at a point where it's undefined, it kind of blows up. It gets really, really big, either in the positive or negative direction. So that's what's happening here. As you get closer and closer to pi over 2, and I should probably graph those lines. Where am I here? There we go. So if I graph y equals pi divided by 2, I didn't mean y, I meant x. There we go, that's better. And if I graph minus pi over 2, all right. So one cycle of the tangent, it's not really a cycle, it's more, I would say period, but it starts here at minus pi over 2 and extends to pi over 2. So one period there is this distance from this point to this point is pi, right? From minus pi over 2 to pi over 2, that distance is pi. So the period is pi. It repeats itself every period. Just repeats itself. And cotangent, let's go ahead and put that in. Because it's the reciprocal, it's going to be the reverse of the tangent. It's going to be in this little region right here, from this point to this point, it's between 0 and 1, right? Well, tangent blows up at in that time. And then when cotangent is blowing up, tangent is between 0 and 1 in this area. So it's kind of, because think of it, if you have a number x, but then you take the reciprocal of that, instead of, if x gets close to 0, what's going to happen to the reciprocal? It's going to blow up, right? Because you're taking 1 and dividing it by really, really small numbers. So that's because they're reciprocals of each other. That's why we have this sort of behavior. So here's tangent. This is the tangent. And then if I get rid of that and cotangent is, the period is not between negative pi over 2 and pi over 2 for cotangent. Instead, it's between 0 and pi. So let me change these to 0 and to pi. And also notice, because of this behavior of these graphs, so here we go, one cycle is between 0 and pi. But because of the behavior, notice we don't really have an amplitude, right? But what happens is these points, like say here at 1, right there, I'm trying to zero into that point. If you're looking at this point here, if I multiply my function by 2, suddenly it's going to go to a height of 2. So let me do that. So it just gets stretched out. So this point here is doubled and goes up to there, okay? But it's hard to see that. Now in your homework for this section 5.6, they're going to give you a function. So they're going to give you like this function, 2 times cotangent x, and you're going to have to pick the right graph. It's a multiple choice sort of thing. So if you're not sure how to do that, just use Desmos to help you pick the right graph when you do those problems. Okay, let me just show you what I'm talking about here. Here's a sample of the types of questions, and these come from section 5.6. Let me go stop sharing my screen and you'll see what I mean. There we go. Okay, section 5.6. You're given a graph. I don't know if you can see that. It says 6 tangent x over 4. You're given an equation and you pick the correct graph. And like I said, you're just going to go to Desmos and help you to pick the right graph. I'm not going to test you on this, okay? This is just for homework purposes because we're running out of time here and it's just too much for you to learn in such a short period. So I'm not going to test you on 5.6, okay? But I will on 5.5, just the A, B, C, D with the amplitude, phase shift, and period, okay? All right, any questions on that? All right, now I'd like to talk about the next section, which is the inverse functions. So we're moving on to 5.7. And we've done a little bit of this already, inverse trig functions. Okay, so the thing you should know about inverse functions. So this is a little bit of a review from algebra. In order for a function to have an inverse, it must be 1-to-1 okay? It must be 1-to-1, and so it must pass the horizontal line test. Do you remember that from algebra? It's okay, I'm telling you now. So if you forget, I'm telling you now. It has to pass the horizontal line test. Well, just so you know, the trig functions don't pass the horizontal line test. So how is it that we are able to find the inverses of these trig functions? Okay. All right. Well, to get around this problem, because we want them to have inverses, because if they have inverses, then it's kind of nice to calculate the inverse like we did with our calculator to solve certain real world problems, okay? So we want the trig functions to have inverses, but we have to kind of fix it so that they do. So we need to restrict their domains. To allow them to be one-to-one. Okay, so let me show you how we do that. I'm going to go back to Desmos again because that's the best way to understand these trig functions. I'm going to give you a moment to finish writing though. That's kind of a lot of writing there, so I'm just going to wait a minute so you can get that. So in order for a function to have an inverse, it must be one-to-one. In other words, it has to pass that horizontal line test. And trig functions don't, so we need to restrict their domains. Okay, going to Desmos again. So what the horizontal line test is, if you draw a horizontal line, so let's just say y equal 1. Let me draw that line. In order for a trig function to be to have an inverse or to pass the horizontal line test, it can only pass once. We have a problem, right? It passes many, many times. Well, if we restrict the domain, then it will fix that problem, right? So I'm going to go ahead and restrict my domain. How do I do that? Well, here's my function, and to restrict the domain, I specify that I want my x to be, for the cotangent, we want it to be between 0 and pi. 0 is less than x, which is less than pi. Okay, and I suppose we could say less than or equal pi. Hold on. There it is. Now it passes the horizontal line test because I'm focusing in on one piece of the function. And so when you use your calculator and you're calculating the inverse of a function, you're just focusing in on one piece, okay? So let's just, this one's cotangent. Let's focus now on the three main functions that we've been working with: sine, cosine, and tangent. So let's get rid of all this stuff here. So I want to focus from 0 to 2 pi. So that's the period. So I'm going to go y equals, oh wait, sorry. 0. And I'm trying to remember, I think for sine, we go from minus pi over 2 to pi over 2. I think that's right. Yes, that's correct. I had to think about that for a minute. Okay, here we go. So we go from minus pi divided by 2. And that is, we're saying that that is less than or equal to x, which is less than or equal to pi over 2. All right, there we have it now. That's what I wanted. I had to be careful that every horizontal line would only intersect that function in one spot. And you can see this one does pass the the horizontal line test. So we're good here. So we're going to restrict the domain for sine and it's going to go between minus pi over 2 and pi over 2. And then for cosine, we restrict it from 0 to pi. And so there you can see. All right. So the blue is the cosine and the black is the sine. And both pieces are going to be in, have horizontal, pass the horizontal line test, and therefore they have inverses. So when we talk about sine inverse and cosine inverse, these functions that I'm graphing are the ones that we're talking about. So let me go back to the dot cam. Right here, sine inverse of x and cosine inverse of x. Those functions are the ones we're talking about, are these here in decimals, okay? The black is the sine inverse, well, the sine function, but we use this one to determine the sine inverse. So let me see what Desmos shows me. I've never actually used Desmos to graph sine inverse, so I'm never, it'll be kind of interesting for me to see that. Okay. Never occurred to me to, let's see. There we go. All right, so let's get rid of the blue for a second here and focus. All right, so here we have y equals sine x with the restricted domain, and here we have y equals sine inverse of x. Notice that if I draw the line y equal x, and I will zoom in so you can see better. One of them is a reflection of the other across that line. So let me zoom in and you'll see what I mean. So the green, if I switch x and y, this piece right here will flip over to the black. And this green down here, if I switch x and y, will flip over to this black. So the green function is the inverse of the black function and vice versa. So you have sine, but it would not have worked if I had not restricted the domain for the sine function. So this is the important point. This domain right here, you have to remember that this is going to come up in your problems later on, okay? And I'm just going to remind you now. It can be kind of tricky. So because again, we're doing this so quickly, I may be careful about putting too many problems like that on there, but on the exam. I'm not exactly sure how we're going to work that out, but all right, now let's do the same thing for cosine. You can see the reflection across the purple line. Inverse functions will always be a reflection across that y equals x, that purple line there. Every single inverse function. Another one that you're familiar with, this doesn't have to do with trig functions, but let me show you. Y equals x squared. Now watch this. This function does not have an inverse. Watch, it does not pass the horizontal line test because it intersects twice. However, if I restrict the domain, and this is pretty cool, if I restrict the domain and say that x has to be greater than 0, now this piece has an inverse. What is that inverse? Well, that inverse is y equals the square root of x. So watch this. And you can see when I draw the line y equal x, they're reflected across that red line. The two functions are. So basically, inverses work that way. One undoes what the other one does. This one squares, this one square roots. So if I take the square root of a square, I will get x back. You put in an x, you take the square root, then you square it, you get x back. Well, that's what inverses do. They kind of undo each other. And they graphically, they always look like this, a reflection across that red line. Okay? So that's exactly what's happening with the sine, the trig functions. However, just remember, we didn't use the real trig functions. We had to restrict the domain first in order for it to work. Just like we had to restrict the domain for this x squared here, which, okay, so it's kind of interesting. Let's do some examples. Now the rubber hits the road here and we'll start to get more comfortable with these ideas here. Okay, so, and then we'll go back to the cosine one. So, example 1. We have sine inverse of sine pi over 4. Okay? What is the answer to that? We're not going to use our calculator, okay? What is sine inverse of sine pi over 4? Remember what I just told you? It undoes, one undoes what the other one does. So if you put in a pi over 4 and take the sine and then immediately take the sine inverse of that, what are you going to get? You're going to get pi over 4. Okay? Sine inverse of sine pi over 6. All right. Well, that's easy. That's just pi over 6. Just like the square of the square root of 4. Okay, you put in a 4, you take the square root, you get 2. But then you square it, you get 4 back. Okay, it's that simple. You put in pi over 4. If you take sine and then sine inverse, you get your pi over 4 back. If you put in pi over 6, take sine, sine inverse, you get pi over 6 back. Hey, we're cruising right now. This is simple. You should have no problem on a test doing this, right? This is easy, easy as pie. Okay. All right. Put in minus pi over 7. I get minus pi over 7. Everything's working great until, there's always got to be a catch, right? Until you get to this spot right here. I had to put a catch in here somewhere. 7 pi over 6. Okay, what is that? Well, I'll tell you right now, it's not 7 pi over 6. Why? Well, because going back to Desmos, let's think about this for a minute. Oh, and of course I erased it, but I'll just have to put it back in. Oh, I don't want to type all that. But remember how I had that let me just do this in my notes. This is going to be hard, take too much time. Okay, so remember I said we restricted, in order to get sine inverse, we restricted the domain of sine, and our input was between, so our x value was between minus pi over 2 and pi over 2, okay? Actually, yeah. All right. Well, we have to have our range in between there. And so this particular angle is not in that. And so we need to convert this to the right, to get it within that range. So let's just graph 7 pi over 6. All right. So remember, we divide up our half circle by 6 when we're doing this. And here we go. You're coming around 1, 2, 3, 4, 5, 6, 7, 6 of pi is right here, okay? That's 7 pi over 6. What are the coordinates there? Well, remember, in this particular quadrant, your x and y values are negative. So this point here is negative square root of 3 over 2, negative 1/2. Remember that on the unit circle? And remember when we calculate our sine functions, we use sine of 7 pi over 6 is the y value. So that's negative 1/2, okay? Well, what angle in this range between, and let me use theta here because that's kind of better. I don't want to confuse this x with this x. It's a different x. So our angle has to be between minus pi over 2 and pi over 2. Which angle has the same sine value as 7 pi over 6? Well, the sine value is negative 1/2. And over here, if we think of this angle down here as negative pi over 2, and this angle up here as pi over 2, the one that has the same sine, let's say, so we have square root of 3 over 2, negative 1/2. Remember, the sine is the y value. Over here, we have negative 1/2, and over here, we have negative 1/2. So they have the same sine value, but this one is the right choice because it's between negative pi over 2 and pi over 2. And so I want this one. Well, what is that? If we're talking about negative angles, which we are, this is negative pi over 6. Negative pi over 6 is the angle that's in the right range, okay? So my answer here is negative pi over 6. So why did these work? Why did pi over 4 work and pi over 6 work and negative pi over 7? Well, because they were all between negative pi over 2 and pi over 2, which sine, since we're working with sine, our angles have to be in that range. Well, this one, this one was not. 7 pi over 6 is out of that range. So we had to convert it to an angle that had exactly the same sine value, but was within the range that we needed it to be, okay? So I think we're running out of time, and I will continue. Well, I think we have a little bit. Let me do one more example. We've got about a little bit of time left, a few minutes. So let me do another example. So it's kind of tricky, but if you understand why it is that way, because when we created sine inverse, we restricted the domain, and that's of sine. And once you restrict the domain of sine, you have to, work within those parameters or that restriction. So the next question says, use a sketch to find the exact value of the following expression. All right, we have cosine of sine inverse of 21 over 9. All right, so I am going to sketch a triangle in the coordinate plane. We're talking about sine. That's we've got sine inverse. Remember, sine is y over r. So our r value is 29. So if I draw this point, this distance here, the height, which is your y, is 21. Let's draw it like this. That's 21. and the radius, or the R value, is 29. So there's my sketch. It said to use a sketch to find the exact value of the following expression, and this is taken right from your homework. So there are a lot of problems in there like that. So I sketched it, but now I have to find the cosine. So I've got my sketch here, and in order to find the cosine, I need the x distance. That's this distance right here, okay? This is your x. So using the Pythagorean theorem, I have that x squared plus 21 squared equals 29 squared. And I can solve for x. X squared equals 29 squared minus 21 squared. And then x equals, and since x is talking about a distance in the positive x direction, I can just know that it's positive. I'm taking the square root. 29 squared minus 21 squared is 400. So when I take the square root of 400, I get that x equals 20. So this side here is 20. Well, now I can calculate the cosine, right? Cosine is the x over the r. So the cosine of this angle, I don't even need to know the angle. All I know is that it's the inverse of the sine inverse of 21 over 29. That's that theta. I don't need to know theta because now I'm going to take cosine of that theta. And that cosine is 20 over 29. All right, that's how you do those problems. You do a sketch. Now, I suppose you could use your calculator to do this, but you're not going to get a fraction necessarily. I think it's going to give you a decimal value. So they want it like this. They don't want the decimal value. So you need to do this, but you could always check yourself on the calculator and see if you get the right answer doing that. Okay, so I'm going to continue with this and finish up section 5.8, and then we'll talk about the test on Thursday. And then that following week, we'll start testing, okay? All righty, any questions or anything? You're awfully quiet out there. Is anybody here? I can't see you guys out there and never. Yeah, you're all there. Hi. Anyway, yeah, if you have any concerns or questions, just contact me by email if you need to, okay? And we'll see you on Thursday.
I have a question.
Okay.
Do we have to memorize the unit circle by the midterm exam?
I did say that you did, but let me reconsider that, okay? I'll think about it. I may just give you the unit circle. I've got to look and see at my test and see if, I don't want to make it too easy because then, you know, this is college, right? But I don't want to make it too hard either. So when I make up the test, I'll decide and let you know, okay?
Okay, sounds good. Thank you.
All right, thanks. Y'all have a good one.